then I'll get started here. I shut the gas off yesterday because there's some leaks on the lines, and I don't want to extinguish all your tanks here, so we're going to get that addressed.
I'm Warren, by the way.
Yeah, I'm Mindy. Nice to meet you.
Nice to meet you too. We've talked on the phone there a few different times. So I did snap a couple pictures of the back connections on the ALD.
Yeah.
So I'll send them to Tom, you know, unless you've already sent them.
Yeah.
But
We were in the meeting yesterday.
that, yeah, we were talking yesterday. Did you have any luck with the TMA ampule?
Yeah, so actually I made inquiry from Tico,
Okay.
and they told us they have it.
Oh, great.
Yeah, that is good. They have it, and we are going to play for
Good. I'll be out of the way.
Yeah.
I did bring this.
That think this will do it if we
Deposition chart. So it's just, here, chart to kind of get it down here.
Oh, my bad. I hope it's
All material, stuttering,
Thank you for catching that.
Yeah, I don't know if the one in Dr. Miyagi class has different different deposition materials, but they definitely have the sputtering machine. We got to see it last semester.
Not to shoot, as you said, this one does everything.
Yeah.
that kind of stuff. But, you know, if you have any questions like that, you can always come to us, or ask the guys.
Yeah, one down, one movies.
Yeah, so, I mean, people sometimes like, yeah, I'm going to get that somewhere, but
Everybody ready? All right. My name is Brian Kendrick, and I'm the test department manager at the Lester Company. I have Mary Ann Griffin with me. She's a brand new test engineer. She's coming to see how we do the installations and help me out. So you guys know Warren. Or A1 sales guy. All right, so I came here today to install the Nano36 sputter tool, and kind of wanted to go over a few things, just point out some components. One thing I wanted to point out is I don't really know this chiller. I know that you guys supplied this chiller, and I was looking at our system utility requirements. You know, we want about 25 degrees C of chilled water. It looks like it's set at 20.
Yes.
So really what we want, we just don't want it to sweat whenever we vent the chamber. So we want it a couple degrees above the dew point. So I don't know the workings of this controller, or else I would change it. But if it starts to sweat, you can pull out the manual. So I don't know what type of water you're using. We usually use straight water, DI water.
Yeah, and DI water.
Okay. All right. I know at times that you have to watch for algae or other contaminants within, but just keep an eye on the chilled water. But I came last evening and got the system operational, applied power. We vented the tool, put targets within the sources, added the dark space shields, added the shutters, put the platinum. I'm going to vent the tool and show everybody how to do those things. But I first just wanted to show some components on the tool. So this tool is glove box compatible. Notice the bolt pattern around the outside of the door here, and I'm assuming you bought that glove box to put on this tool at some point forward. So we have two doors on this tool. This door, sometimes in the back we have a blank, but that also has door access, kind of like a submarine hatch. So once you vent the tool, you loosen this, there's a ball screw, the door will slide out. You don't have to crank it the whole way, you just have to get a gap of separation within there, and then you grab this ball and you kind of open it and it gives access to the tool. We'll go through and I'll show you how to do that. But this chamber, it's a smaller chamber. It has a couple different features I wanted to go over. So you have a 300 liter per second turbo pump, 3-position high back valve. You have an ion gauge. This ion gauge may be easier to see from the side. There's some scrolling displays on it, so it'll show you the system pressure. Whenever the high back valve is open, the ion gauge is activated. When the high back valve is closed, we run off of the convection gauges, which are which is right here, which is basically on the same line as where this gauge is, and this is our 4-line gauge. So if you kind of look here, you'll look at the 3 gauges, IG, CG1, CG2. This is your convection gauge. This is the second convection gauge.
This is the iron gauge.
This is the iron gauge.
So here we have what parameter can be shown here?
Yeah, so right now it's showing the convection gauge pressures for both the 4-line and the chamber.
Yes.
And the filament is enabled because the high back valve is open. I was telling Marianne earlier, when we vent the tool, I may loosen this and rotate this 90 degrees so you can see it from the front. Be a little easier. So just wanted to show you that. So if you look back here, the door's the same as in the front. It swings the same way. We have the ability, we can switch this hardware around, have it swing the other way if you need it to be. But I took this, or I had Marianne take this cover off. I wanted to show you some components within here. So here's your cooling lines. On the incoming lines are blue. That's Wesker standard. The return are red. And our flow switches are always on the return side. We want to make certain that the cooling water goes through the component, and then we achieve the flow rate we need after it goes through the component. And these flow switches are important because if they're not made, we prevent the power supplies from turning on. So we don't want to damage anything. But another reason I wanted to show you the back of this is that you have 2 isolation valves, and whenever you turn these valves on, you get full flow. There's no way to throttle between, you know, each of these individual circuits or legs. There's also some components back here I wanted to show you. So in the front of our tool, we have what we call a Rigel controller. The output of the Rigel has basically D-sub connectors that we use pre-molded cables that we plug from the output of the Rigel to these bricks. And so this is the cooling brick. So this is an input brick. Each of these flow switches go to here, and if we have the required flow set point, we get a LED which illuminates saying that is satisfied. We also have a mass flow controller brick. Within this brick, we have the 2 mass flow controllers, which we'll speak about in a moment. Capacitance manometer, and what is this one here? Cap man 1 cap. So this is the input, and the others go to the capacitance manometer. I'll explain where these components are. But I really wanted to point out these mass flow controllers. If you look at the flow controllers, it says F100 and F20. So what that is F100 is a 100 skim mass flow controller. That's the master controller. And F20 is a 20 skim. It's a slave controller. So if you're doing metal, if you're doing oxides or nitrides, you always want to first run off your first mass flow controller, and then bleed in a small amount of nitrogen or oxygen on the second one. And I'll show you how to operate that via recipe. So right now you have everything hooked up into argon, but in the past you have argon going to mass flow controller 1, and whatever your nitride or oxide, whatever gas you want to have going into the second one. Also within here are some pneumatic solenoids. So you'll notice on this tool there's a lot of this, I think it's this 4mm black tubing. The tool basically runs off of compressed air. You go through a solenoid block. The solenoid block is mapped to the output of the controller, to what signal we want to use. And these solenoids, if they're on or active, you'll see there's an LED. It's called up. It's on. Whenever there's no power, these are a single detent solenoid. So when it's energized, it's going to move a spool within. It's going to permit air to travel to that component. When you de-energize it, it's basically a spring return, which will close it off. So really simple to troubleshoot. If you ever have a problem, I start at the very end. I pull the air line off and hold it, hit the button, does air come out? I work my way back.
So we have 2 inert gases, argon and nitrogen, for this device, which can be used depending on the target and materials we want to be touching.
Correct. Yep. Yeah, but right now it's just all hooked up to argon. And whenever I first powered this tool up, what I like to do, because this line's exposed to air, I go through the software and I systematically open up the valves and the mass flow controllers, and I pull a vacuum back to an isolation valve. I was not able to completely evacuate these lines, so we got to fix some leaks.
Yeah.
So
there's 26 connections there instead of the 2, so yeah, I'm sure I got to And I didn't put dope on any of them. They're just Teflon tapes. So
Okay.
I've got pipe dope in there. I can go back and redo them a few times.
Yeah, what I would do is, you know, I would use Tygon tubing if you could, and then use swage lock connectors.
Okay.
So you can use a swage lock to VCR, and the swage lock, they have a barbed insert you can push into the tube. So when you squeeze down on it, it doesn't collapse the tube. It keeps it the same diameter.
Okay.
But yeah, I just wanted to show you the components within here because these are, you know, you really shouldn't have to access this, but it's nice to know how the system operates. So these mass flow controllers, inboard of the mass flow controllers are 2 isolation valves, and they're normally closed valves.
Okay.
So they're labeled MFC1 and MFC2 ISO. A mass flow controller by design is not a positive shutoff device because of the poppet valve within there. It's not going to positively seal. That's why we have isolation valves upstream of that. So in the back here, this is our power distribution unit. So this is a single phase unit. So you know, this is a green mains power right on. And then I have a electrical drawing package that I'm going to give you, and it tells you which circuit breaker basically activates which component. So I don't have all these turned on because I don't need to. Wouldn't hurt to have them on. But if I took this panel off on the bottom of this unit, there is an IEC connector. It kind of looks like it's like a goofy computer plug that's square and has it's a rectangle and has the corners cut off. It's a female socket,
Right.
and they go to the respective circuit breakers. So I don't know what your lockout tagout program is. Worst case, you know, we actually do sell circuit breaker locks, or you could just pull the plug out and put a cover over top of it.
Right.
So stainless steel chamber, ion gauge. This is a I don't know the manufacturer of this valve. It could be a VAT or an HBA, but this is a 3-position valve. So it's open, closed, or throttle, some position in between. And you notice here there's a neural thumb wheel. There's a set screw right where my finger is. So there's a certain way that we set the throttle on these tools. We typically flow 100 skins of gas, and reading from the capacitance manometer, which is over here, we will adjust this valve, the position, so we get as much conductance as we need to get 15 millitorr pressure. And the reason we do that is, do you guys have any sputtering experience?
Very little.
Okay, so RF and DC. DC you can sputter with very low pressures, as you can RF, but it takes a higher pressure to light RF. Typically you can light DC between 3 and 5 millitorr. RF type sometimes takes up to 50 millitorr. But we found that, you know, 15 to 20 we can really get it RF lit, and then once it's lit we reduce the pressure so we can get to, you know, we get as much gas out as we can, and we open up the mean free path and get work to happen. Basically material sputtered off. But I'll show you how we do it, and it'll once I open up the software, I think it'll be pretty intuitive. So turbo pump, water cooled turbo pump, 3-position valve. This chamber gets a little warm. That's why they have this guard over top of it. You have, I believe, 350 degrees C heat on this pool. I'll check the spec. So this is the power lead that goes into the heaters. This is just a straight DC motor for rotation. And then this is your thermocouple lead. So this is 2 thermocouples in a single sheath. So there's 2 of them within here, and there's a vacuum seal here. So you'll notice, I think one of them is labeled process, or sometimes they label process and over temp, but it's basically TC1 and TC2. TC1's your process thermocouple, TC2's your over temp. And I'll explain how those work. But it's a pretty concise package. It has a lot of capabilities. I'm going to show you in the back here. Let me get out of here. You can take a picture of the back. But that's where the force guns exit the bottom of the chamber. And there's a couple adjustments we can make on the force guns. So they have a larger version of this back coupling that you can insert those in further, well down, change the throw distance. You can rotate them so that they're, I kind of think of a clock, where the clock hands are in the center. You always want the gun to face center. You don't want it to be indexed offward, so we have the ability to have it turned off access if you need. And we can change the actual angle of the gun. and the angle of the gun has an effect on uniformity. So whenever we had the system, there was a couple of specifications we had. One was to make a certain base pressure. I think that was 9/7. I'll show you on your desktop. I put all the test files that we utilized. I'm going to give you hard copies of those also. And I'll give you the films that we had run, the powers, the pressures that we ran, and what our results were over the wavelengths. So we use a P17 step profilometer. We calibrate for our metal films. Anything that's thin enough for SiO2, we use a spectral reflectometer, the filmetric shield, and yeah, it's we get pretty good results from it. So yeah, it's pretty concise package. Gradual controller. A couple things on this I wanted to point out. You'll notice that we have what we call a light tower here. There's a red, yellow, green, and blue LED. Kind of difficult to see. So if you look here, this is really the same. So this emulates the same thing. And those LEDs have a certain indication. Error report, if there's an interlock or a warning. If everything's happy, it's green. It's running a recipe for blue. So just wanted to show you how those two correspond. Also on the front of this controller, you'll notice that a couple LEDs that say that the power supplies within are sound. So you have a 12-volt supply and a 48-volt supply. The 12-volt, I believe, is for the majority of the solenoids. I actually thought they were 24. I could be wrong, but the 48 is for the turbo. So we have a 48-volt turbo controller. This tells you your main power. This is the same as in the back, that LED, or that at least light. And this is our AC power, is correct. Single EMO, and there's a start contactor here. So I'd like to vent the chamber, show you how we vent it, shut it down completely, start it back up. You may have a power outage. You need to know how to get the system live again.